Nice. Cool. Yeah. So I guess just to recap, like what we've been hearing about all week is fault-tolerant quantum computation, which is when we take a logical circuit and we compile it into a physical circuit, such that the logical circuit is what we want to run, and the physical circuit is what we can run and get the right output, even when errors happen during the execution of the physical circuit. So we basically want to construct this compiler to have like a physical circuit that's as efficient as possible while still computing the logical circuit in the presence of noise. And often what kind of people do to like compile these logical circuits into physical circuits is to develop like ways of performing Clifford gates fault tolerantly on quantum LDPC codes, and then kind of teleport in some non-Clifford resource states. So we saw a lot of examples of this early in the week. There's no reason this is what you have to do, but like a lot of really promising proposals for quantum fault tolerance at this point seem to be based on this general paradigm. And kind of something that makes this tricky, something that really bottlenecks the performance of these protocols, is that the preparation and teleportation of these non-Clifford gates is actually like somewhat intensive. You first need to like prepare a high-quality non-Clifford state and then teleport it in. And various proposals are bottlenecked by various things. Like historically, preparing the resource states was tricky. Now it seems like there's some pretty efficient ways to prepare these states, but it can still be tricky to like teleport them in really quickly. But kind of at a high level, I think it's still somewhat difficult to really efficiently perform these non-Clifford gates. Yeah, so I guess something that could really kind of change the game at this point is if we had LDPC codes that can just natively perform non-Clifford gates. So if we had like pretty good quantum LDPC codes where we could just perform some constant depth circuit, and that would just implement like a lot of non-Clifford gates, a lot of logical non-Clifford gates, then we could kind of change our whole paradigm. And instead of kind of preparing these resource states and teleporting them in, we could just do our whole computation in these LDPC codes. And every time we need to do a non-Clifford gate, it's actually super cheap. We could just like apply some constant depth circuit. Yeah, I'll also mention later on, I'll mention some other ways of still using these codes with non-Clifford gates, but kind of in more of a similar paradigm to this like resource state preparation idea. But suffice it to say, like these LDPC codes supporting non-Clifford gates natively would be really useful for fault-tolerant computation, for lowering the overhead of fault-tolerant computation. But current constructions are really far from optimal. If you compare parameters that we know of for LDPC codes supporting non-Clifford gates to just the best LDPC codes we know of that don't support non-Clifford gates, the gap is huge. Kind of we still have a long way to go to make kind of this idea practical. Right. So in this talk, I'm going to be kind of looking at some constructions of these quantum LDPC codes with transversal non-Clifford gates to kind of slowly kind of close this gap and bring them more towards regimes where they're competitive with other techniques. But I should first define like exactly what I mean by a quantum code supporting a non-Clifford gate. And in this talk, I'll focus on the CCZ gate, which is, I'll define in a little bit, but you can think of it as just like a canonical example of a non-Clifford gate. So we say that like actually a triple of quantum codes supports a non-Clifford, a transversal CCZ gate. If so, these three codes encode three different messages, and we say these codes support a transversal CCZ gate if there exists a constant depth circuit of physical CCZ gates. So maybe we'll first like do CCZs just along like every three respective qubits across the three code blocks, and maybe we can do a second layer of CCZ gates like diagonally, but some constant depth physical CCZ circuit. And we want that to induce, we want that to preserve the code space and induce logical CCZs on the underlying logical qubits. So if we have a concept physical CCZ circuit that induces logical CCZs, we say this code supports a transversal CCZ gate. And We want the physical circuit to be constant depth so that errors can't propagate very far or accumulate very much during the physical circuit. We want the logical circuit to actually also be like low depth, or at least to have many disjoint triples of logical qubits on which we're applying CCZ, so that we have like good control over the logical action induced by the physical circuit. So you can see like if our physical CCZ circuit induced like this logical circuit I've drawn here, then basically all we could do with this code is like apply this like really weird looking logical circuit, which would be like somewhat tricky to make use of in general. So we'll allow ourselves to like zero out some of the logical qubits, but then we want to kind of zero some of the logical qubits in a way that on the remaining qubits, we have as many as possible logical CCZs on like disjoint triples of logical qubits. So this isn't always necessarily what you want, but it just gives you like a very nicely structured logical circuit. So it's usually what we're looking for. I guess I can also add, like, if you're using transversal gates to prepare magic states, then you usually want just a bunch of disjoint CCZ states, which means you just want to apply a bunch of disjoint logical CCZ gates. Okay, so that's what a transversal CCZ gate is. Yeah, our code supports a transversal CCZ gate if it has this property. So our main results are a couple families of codes supporting transversal CCZ gates, and in particular codes with fairly high rate. So I'm able to just put all the parameters up. So we give a family of quantum LDPC codes with like almost constant rate. So the number of disjoint logical CCZs is n to the 1 minus epsilon. And the locality, or like the check weight, is constant. And the distance of these codes is roughly the cube root of the block length. So the distance is still not optimal, but the dimension is pretty high. And we also actually can push the dimension, or like the code rate, all the way up to constant. So we can get a linear number of logical CCZs. But then the codes are not quite LDPC. They have locality like n to the epsilon for an arbitrarily small constant epsilon. So I'll now just kind of briefly flash a bunch of parameters of other works that have studied this question. So Guanyu had this really nice paper getting like distance and dimension n to the 1/2. This work Z1 mentioned yesterday, this very recent work, used some really nice ideas to get the distance all the way up to almost linear, but on a constant number of logical qubits. Actually, in a prior work, we had roughly similar parameters to the first construction above, though the locality was polylogarithmic instead of a constant. And if you don't require the LDPC condition, a lot more is known about constructing good codes with CCZ. And I should say there's been like all these works build on like a very nice line of works going back to like Hector Bombin with like transversal gates on the 3D color code. So yes.
So K is the number of qubits on which you get these disjoint logical CCZs, and it's not the number of logical qubits you have.
Thanks. That's a super important point, which I forgot to say. Exactly. So often usually when people say like NKD, they mean a code of length n with k logical qubits and distance d. Here I'm using k to denote the number of disjoint logical CCZs you can do, or like the number of logical CCZs you can extract from your physical circuit, which in the context of transversal CCZ gates, it seems to be what we care about most of the time. So in this talk, it's cleanest to write that. But yeah, so if you compare like these results with what some of the papers say, like these codes are like actually constant rate. It's just that you can only do a CCZ on like a constant number of the logical qubits. Yes.
These are all like cable. Take the quality of
Oh, sorry. Yes. So locality. So I'm not considering geometric locality at all. I'm just considering like, yeah, the degree of the Tanner graph, like the number of like qubits every check talks to. So yeah, so locality here, it's actually. Yeah, it's like, yeah, stabilizer weight. Yeah, like K local.
In terms of this K, just right now, CCD is just my understanding, like you need more eventually, right? You want some type of addressability where you can kind of say, like, some amount of overlap, right? Because like someday you might want that, right? If you want to go to perfect, right?
Right.
Is that correct? Or,
Yeah, so that's a good point. So yeah, once you actually want a fully fault tolerant computation, like sorry, a full scheme for universal fault tolerant computation, then yeah, you do want to be able to do gates across different qubits in overlapping ways. So I guess a couple points on that. First, in this talk, I'm just focusing on the CCZ aspect, so I won't be talking about like getting universal computation. But it turns out that actually getting this like universality is in some sense the like easy part, at least from an asymptotic perspective. One reason for that is that actually I won't talk about it, but all of the constructions I'll describe just naturally come with addressability. It turns out that there's like code automorphisms and there's ways to like select out just certain logical CCZs. So it turns out addressability is actually not that difficult once you have like the CCZ construction here. And also like you can also just, as I'll say on the next slide, you can use these codes just to prepare resource states. And then you just want to prepare resource states sufficiently as possible.
So, what is the motivation? If you want to define a better statistics, it does take for a while, and you know that high distance home activities. Other aspects, like other than.
Oh, like as in what you want out of the code?
So what's the motivation?
Oh yeah, what's the motivation? No, that's a great question. So actually, I'll get to that in the next slide. So I should say, no, perfect. Yeah. So in terms of like what you need for like fault tolerance, at least in theory, just protecting against like locally stochastic noise, I think you're totally right. Like there, we really want to optimize, like have the rate like k be as large as possible, while maintaining just a reasonable distance. Like polynomial distance is fine.
Yeah, I feel like your number is
Yeah. So I think I agree. As I'll say next, like yeah, for doing these gates in practice, like the high rate ones are what we want. I think so in especially in like practical systems, often I think you do care about having the distance be large, just like hyper-F product codes have a constant rate and square root n distance, but they somehow don't perform as well as like lifted product codes just because at small sizes the distance does kick in. So I think practically you could see the motivation, and then also just theoretically it's like an interesting question. Yeah, I will also point out something you can always do with one of these codes is take a smaller block and repeat it a bunch of times. So in that sense, like for instance, this construction is like almost a strict improvement on this construction, because if you repeat square root n blocks of this construction of size square root n, you get like n square root n and like square root n over polylog n. So you can always like interpolate between these parameter regimes. Oh, great. So yeah, so actually kind of related to some of the questions, I will say a bit more about why we really care about the high rate codes. So kind of, even though we lose a bit on distance compared to some of these other constructions, what we really want is to like maintain a reasonable distance while getting k, like the number of logical CCZs, as large as possible.
For the disjoint logical CCZs, does there exist a basis where it's just like randomized, or do you have to post?
Oh yes, great question. Yeah, in our construction, there's actually just a nice basis. So yeah, you don't need to like apply some weird Clifford. Oh, cool. So yeah, so one implication of like our constructions at the top here is low overhead in a space-time sense. So like low space-time overhead magic state preparation. So this is kind of going back to this problem I mentioned at the start, where like a lot of the time that people want to do non-Clifford gates, they'll prepare resource states and then teleport them in. And this setting is just the simplest because it's kind of more direct to like compare different schemes. And kind of traditionally what people would do to prepare these magic states is something that looks like this. So it's actually fairly complicated. They would use non-LDPC codes, which like do not natively like have really easy fault tolerant error correction. So people would kind of have to concatenate some code supporting a CCZ that's not LDPC with some different code that might be LDPC that supports fault-tolerant Clifford gates, but doesn't support a CCZ. And then they kind of like do some repeated distillation where they like teleport in some noisy CCZ states to like transversally implement this CCZ in a concatenated code, and then distill out some like less noisy CCZ states, and maybe repeat this. So this is like traditionally what people have done. Since then, people have come up with like more efficient things in practice, like magic state cultivation and so on. But even then, it seems like you might still need to do some of this distillation. I guess yesterday we heard about a lot of the more like cultivation-like techniques. But something that you could hope to do that would be just really efficient would be just to use quantum LDPC codes with transversal CCZ. Because then you can just literally prepare your code, like just prepare a bunch of plus states in your code. And often these codes like have fairly efficient ways to prepare plus states. And then you could just do like your physical transversal CCZ that's like a constant depth circuit. And all of a sudden you have your magic states. So our codes like can prepare like n to the 1 minus epsilon of these magic states using this. If you could increase k all the way up to linear and n, you could literally have a scheme for like constant space-time overhead magic state preparation, which would be like asymptotically optimal. That would be kind of the dream. And so we're kind of getting like almost there in the sense of like we have n to the 1 minus epsilon, and we'd want to bring that all the way up to n.
Question about that. Does that require like fault tolerant state preparation or something to control?
Oh, yes. So actually, in what I described, it does. So yeah, so this is like something you could obtain if you had some other pieces. I think actually there are ways to like still concatenate with a code with another code and actually not even need fault tolerant state prep. So that's like somewhat more involved. So yeah.
So do you have like does it work up, or is it easy to like extract like each CCD state?
Wait, sorry, could you say that again? Does it have
Like your CCD like have like this joint set of like plus state, or does it have like a local one?
like the logical CCZs?
Yeah.
Or the physical?
Physical.
Oh, sorry. So we're running so this circuit is physical. So this is just some physical like constant depth circuit. And then what we get out is a bunch of like CCZ states on disjoint triples of logical qubits. I mean, actually, yeah, the physical circuit, you can always make the like actually depth 1 by just like concatenating with a constant size repetition code.
I guess like something else you could add, like, even if it's on disjoint triples of logical qubits, you might like want the logical operators to also be kind of disjoint, so that's easy to like selectively pull out one of those CCDs. Is that also possible?
Right. So yeah, so if we want like a linear number of CCD state, like kind of constant rate and polynomial distance, we'll necessarily have some overlap between the logical operators. Though I guess so. Yeah, so I won't talk about like how to exactly fit this into a fault tolerance scheme, though these codes are all like hypergraph product codes that we're talking about. And these are hypergraph product codes are generally have like reasonably efficient ways to like extract qubits and so on. So in practice is maybe like as good as you could hope for, optimistically, I guess. All right, cool. So yeah, so this is kind of a motivation for why we really want these like high rate LDPC codes with CCZ. As a small aside, like if you've like followed the magic state distillation literature and like have heard about this parameter gamma, like log n over k over log d, it's kind of like a rough indication of like how good your code is at preparing magic states. It used like a kind of old protocol that's not what I'm showing here. It's more like this thing. So it's not a great measure, but roughly speaking, like the smaller this value log n over k over log d is, the better your code is at preparing magic states. And for a while, it was like a long-standing open question to get gamma arbitrarily small. And these codes are actually the first known LDPC codes with gamma arbitrarily small. Cool. So if that was all just a lot, I think the upshot is that we construct some improved like LDPC and also almost LDPC codes with Transversal CCZ. We're still not close to asymptotically good. And so now we'll just spend the rest of this talk talking about how we actually construct these codes. Cool. So I actually never defined the CCZ gate, so I should do that now. It's just a 3-qubit gate that takes its input 3 like qubits x, y, z and flips the phase if all 3 qubits are 1. In other words, it introduces a phase of like -1 to the x times y times z. Okay, there's also this QID version. So the QID version, it looks similar. There's like a finite field trace. In our constructions, we'll actually have to work over finite fields for some like larger finite fields in F2 for some technical reasons. But for this talk, you can really just think about the qubit version, if that's simpler. And really, we should be thinking of the quantum CCZ gate as a quantum analog of like the classical multiplication gate, which like takes 2 bits and outputs their product. And you can think of like the Toffoli gate if that's more intuitive, because Toffoli is like equivalent to CCZ, where we like dualize the 3rd qubit by a Hadamard gate. Because then Toffoli literally just takes 2 qubits, multiplies them, and adds them into the 3rd. And you can see like the CC gate is actually literally performing multiplication in the phase. So this is like a very literal, we should take this comparison very literally, because we're actually going to construct quantum codes with Transversal CCZ by constructing classical codes with like a multiplication property, which is like a classical analog of the quantum Transversal CCZ property. And so these 2 families of codes are really going to be analogous. So what are these classical codes with multiplication property? So we say 3 codes A, B, and C has a multiplication property if we take any code word in A and we multiply it pointwise by any code word in B. So the product code word is like A1, B1, A2, B2, all the way up to A and Bn. We want this pointwise product code word to lie inside the code C. If that's true for like every pair of code words in A and B, then we say A, B, and C have a multiplication property. So it's actually surprisingly hard to construct classical LDPC codes with a multiplication property, even though it's a fairly simple definition. So the repetition code definitely works, because if you like multiply all zeros or all ones with another all zeros or all ones string, you just get the product of the 2 strings. The problem, of course, with repetition code is that the code, like the number of logical bits is 1. If we want to increase the number of logical bits, we can actually move to codes based on evaluations of like low-degree polynomials. And on the next slide, I'll describe exactly what these are. But we can actually bump the parameters all the way up to like n, and then the number of logical bits is n to the 1 minus epsilon. The distance is also n to the 1 minus epsilon. So on the next slide, I'll describe what these codes are exactly. But somehow this is like, and epsilon here is an arbitrarily small constant. Somehow this is like, as far as I know, basically the best known construction. There's other kind of, there might be ways to like improve some constants here. People actually thought a lot about this question classically, and yet it seems to be really hard to bump the parameters all the way up to like truly asymptotically good. And one way of like stating the key challenge, like if you think about it, we know a lot of asymptotically good constructions of classical LDPC codes without the multiplication property. What becomes really hard when you add in the multiplication property is that the technique that we usually use to bound the rate of good classical LDPC codes is just kind of like count constraints and argue that the total number of like linear constraints is less than the number of variables. So we just do some dimension counting and conclude that our code is like linear dimension. Somehow, like once you impose what the conditions you need to have a multiplication property, this ordinary constraint counting that bounds rate just totally breaks down. And it seems like a really fundamental problem. So that's why, like, to get around this problem, the only constructions that I know of, at least, like, use some pretty involved algebraic structure, or at least they're like highly structured codes. So then we can kind of use this algebraic structure to ensure a reasonably high rate. But yeah, even just purely as a classical question, I think this open problem is really interesting. Okay, so how do we construct these like almost good LDPC codes with multiplication? We basically define a code where the code components, or like the bits in the code, correspond to points in some high dimensional vector space over a finite field FQ. So like some vector space FQ to the T. So we have a symbol in our code for every point in this vector space. And then we have a constraint in our code for every axis parallel line in FQ to the T. And we just require the restriction of our code word to every axis parallel line be equal to some low degree polynomial over our field FQ. You actually don't need axis parallel lines here. You can also do just like use non-axis parallel lines. And this prior work I mentioned did use some more general lines. But in this talk, we're actually just going to use axis parallel. That's going to be really important for getting like truly LDPC codes with like reasonably high rate. So like if we fix Q, the field size, and just let T grow, we let the dimension of the vector space grow. Then we get these like LDPC codes with almost good parameters. If we kind of let Q grow very slowly, like as polynomial in the dimension of the vector space, then we can actually bump the distance up to like almost linear, even up to linear. But then the check weight becomes longer because now our lines have growing length as we increase the dimension. And the third regime that's interesting here is if we just actually let T, like the dimension of our vector space, be a large constant, and then just grow the field size. Now our check weight grows as some small polynomial because we're growing the length of the lines much more quickly. But then we can get asymptotically good parameters. So these are how we construct the classical codes with multiplication property. So the only missing piece is mapping these to quantum codes with transversal CCD. And to do that, we show this theorem, which is that given classical LDPC codes, say of length n, dimension k, and distance d, with a multiplication property, then there exists quantum LDPC codes with transversal CCD gates, where the quantum codes have length roughly n cubed, number of logical CCZs is roughly k cubed, but the distance is roughly d. So you can see the distance isn't growing as quickly as the length in the dimension. And there are a few asterisks here. So first, this theorem doesn't apply for, or at least we don't show it for fully general classical LDPC codes. We assume that our classical LDPC code comes by imposing some constraints given by local codes within like a graph. So we assume that they're like Tanner codes with local code constraints imposed in a graph. So what that means is that we stick a bit of our code on every, like a physical bit on every edge of our graph. And then we stick like a small local code at every vertex. And the constraints just say that the bits that are seen by a vertex corresponding to the neighboring edges must form a code word in our local code. So we just have a bunch of constraints living at vertices, requiring that the bits it sees along the neighboring edges lie in some local code. It turns out that like most of the constructions of classical LDPC codes with multiplication property that we know of have this structure. So it might seem like it's kind of restrictive, but it actually doesn't really restrict us in practice for applying this theorem. Yeah, I also wrote the theorem for like LDPC codes, but it also applies when like the graph degree here is slowly growing, so then the codes are like almost LDPC. I should say it's also K here is also not exactly the dimension of the classical codes. You could, if it were, you could construct some like kind of annoying counterexamples where you have like say C1 and C2 have totally disjoint supports. So then they have like a trivial multiplication property where C3 is just the zero code. So we actually require K to be like the size of the intersection of information sets. But again, in practice, this isn't like a huge issue. And yeah, the transversal gate has constant CCD, physical CCD depth, and it gives us K-cube disjoint logical CCDs. Okay, so at a high level, the proof goes as follows. We take our classical codes and we map them to one-dimensional chain complexes, and we take tensor products of these chain complexes to get quantum codes. So this is like the hypergraph product construction. It's kind of a standard way at this point of constructing quantum LDPC codes. And then we map the multiplication property to a transversal CCZ using a cup product, which we heard a bunch about yesterday. And I'll go into more detail on like how we do these steps later. But you can see like from the multivariate multivariate polynomial evaluation codes I described, we can immediately obtain like the main families I mentioned at the start of the talk. So first, just as a sanity check, if we apply this theorem to like a repetition code, we basically recover like the fact that the 3D toric code has, or like the 3D color code similarly, has a transversal CZD gate. So that's kind of a nice sanity check. If we apply this theorem to our LDPC, like almost good polynomial evaluation codes, we get our quantum LDPC codes with transversal CCZ that have almost linear dimension and distance roughly n to the 1/3. And if we apply this theorem to our good but almost LDPC codes, then we get constant rate LDPC codes with CCZ, though the distance is now n to the 1/3, and also the CCZ depth of these codes, like the depth of the physical CCZ circuit, is like n to the epsilon. Yeah.
Make sure I'm understanding here. You're always, even though the theorem is more general, are you always imagining applying it where C1, C2, C3 are the same C?
Oh, great question. Yeah, so actually that's true for the repetition code. Sorry, that's a really, I should have clarified this. So that's true for the repetition code, but actually basically can't be true for any other code. Because when you take C1 star C2, like the pointwise product of two codes, you'll like grow the code because you're now taking products of code words. So I think there's I don't remember it exactly, but I think there's a somewhat simple argument that says like if your code is not a repetition code or just like a direct sum of repetition codes, then when you take the pointwise product of two codes, you necessarily end up in a larger code. I think something like this is true.
Okay, so when you're getting your codes with transversal CCD, it's actually a triple of different codes that have a transversal CCD between the three of them.
Exactly, yeah. So I guess, yeah, so in practice, so when I say like, oh, we take these codes, we really just take C1 equal to C2, and then C3 is like the same construction, but of a higher rate, like of a higher polynomial degree. It turns out that you can actually like fold you can actually do it to 3 copies of the same code usually. Or at the very least, you can just take your 3 codes and paste them together and view that as a single code. But yeah, like in everything I'm describing, you should think of just 3 different code blocks.
Do you take the third code to just be fine, but kind of like containing all the stuff that it has to contain, or do you take it to be something bigger than?
Oh yeah, so you can actually do either. It doesn't really matter. Actually, they might even be the same because so we'll typically like here have our C1 and C2 will be like evaluations of polynomials of like multivariate polynomials of individual degree, some bound like L, individual degree most L. And then C3 will be like polynomials of degree like 2L. And when you multiply 2 polynomials of degree L, you get one of degree 2L. Oh yes, yeah. Sorry, I should have clarified that. So yeah, it's literally just hypergraph, like 3-dimensional hypergraph product codes. Ooh. Oh, so how do we prove this theorem? This is still the main missing piece. So how do we construct like the transversal CZD from multiplication property? So this is where cup products come in. So we heard a lot about these like yesterday, though in this talk I think the setting is a bit different in that I'll actually try to give like a non-topological view because I really want to show just like how directly the multiplication property translates into the transversal CCD. So all the intuition, like originally really comes from the cup product, comes from the topology. But we can actually think of cup products for the purpose of this talk as really just a quantum version of just classical multiplication. So just to kind of introduce a bit of notation, just so we're all on the same page. So we'll be looking at quantum codes as chain or like cochain complexes in the standard view where qubits lie at some level I of the cochain complex. And then we'll put Z stabilizers at one level up, like I+1, and X stabilizers at one level below I-1. And the fact that X and Z stabilizers commute is just saying that this is a cochain complex, so that the composition of any two consecutive co-boundary maps between these spaces is 0. So the cup product, it gives us a way to multiply cochains. So I should have said, sorry. So a cochain complex here, it's just kind of like a sequence of vector spaces, AI, where there's these co-boundary maps between every consecutive pair of vector spaces, satisfying this this condition that the square of the co-boundary map is 0. And so the cup product is going to give us like a bilinear mapping from cochain complexes A and B to a third cochain complex C, which like respects the code space or respects cohomology, which I'll define in a second. But it's going to be really like a quantum analog of classical multiplication. So formally, a cup product is just a linear map from I cochains of A and j cochains of B to I plus j cochains of C, satisfying the following Leibniz rule. So the rule requires that the co-boundary of A cup B is equal to the co-boundary of A cup B plus A cup, the co-boundary of B. This is also only over F2, so only over fields of characteristic 2. If for general fields, you need like an additional sign here. And this actually ensures that like cohomology or the code space is preserved. So in particular, just from this formula, you can see that if A and B both lie in the kernel of our co-boundary map delta, then so does A cup B, because kind of this first term is killed off by co-boundary of A. The second term is killed off by co-boundary of B. And also, if either of them additionally lies in the image of delta, then so does the cup product. Again, you can just check that from the formula. So this actually just by definition means that the cup product gives us a physical CCZ circuit that preserves the code space. I'm slightly omitting some details. You also need to like choose some cycle at some higher level. But kind of what the upshot here is like often if you have a cup product on cochain complexes, then the associated quantum codes will have a physical CCZ circuit, like a transversal CCZ circuit, that looks something like this. We'll like apply physical CCZ to any triple of physical qubits whose cup product is 1. If the cup product of our physical qubits is 0, we won't apply a physical CCZ.
I1 here, is this cochain?
Yeah, sorry. I should have been more formal here. So really, this is like, no, that's a good question. So really, what we're doing is A cup B cup C is actually a cochain, and we're like, yeah, I should have written like sum over all the entries of this cochain, or really choose some cycle and then take the dot product with that cycle. Yeah, sorry. Yeah, sorry. So this is like really informal, but morally speaking, like, yeah, if we have a cup product among 3 cochain complexes, it gives us a way to like multiply 3 cochains and preserve the code space. Okay, so let's say we have 3 classical LDPC codes with a multiplication property. We can map these 3 LDPC codes to 3 one-dimensional cochain complexes, essentially just by taking the parity check matrix of each classical code and making that the co-boundary map of our 1D cochain complex. So for instance, this like script A cochain complex, A0 is just like the space of all bit strings of length n. A1 is the space of like all possible syndromes. And then delta A here is just the parity check matrix. So the kernel delta A is the code space of our classical code. oh yeah, so that's what I said. And then it turns out that like if these classical codes have a multiplication property, we naturally get a cup product between the three cochain complexes to a fourth cochain complex that's related to the original three that basically just multiplies our cochains or multiplies like the code words of our classical codes. There's like a couple details here, like for some technical reasons, we want to dualize this third cochain complex, C. And we also aren't, so if we have something in A0 and something in B0, we can often just multiply them pointwise. If we have something in A0 and something in B1, then kind of the dimensions don't match up. So we kind of need to apply some like local transformations to the cochain A0 before we can take the pointwise product with a thing in B1. So I'm slightly simplifying, but like morally, we're really just kind of pointwise multiplying cochains in A, B, and C to get a cochain in D. And this will like satisfy the Leibniz rule. And yeah, the proof of the Leibniz rule is really just will follow from the multiplication property of these classical codes. So this is making progress, but if we ultimately want quantum codes with, so since we already have a cup product, you'd already say, you might already think, all right, we now have our transversal CCZ gate, like we should be good. But these classical codes will not protect us against fully general like quantum errors. Because like if you have a one-dimensional cochain complex and you try to use it to encode a quantum code state or like a quantum state, then you'll either have like trivial distance against X errors or against Z errors. So you won't get like a good quantum code. So instead, we take hypergraph products of these classical codes or of these 1D cochain complexes. And in particular, we want to take the tensor product of all three of our classical codes. And then we do that kind of with all three different cyclic permutations of the three classical codes to obtain three quantum codes. And what's nice about this construction is you can see like within each column here, we have a cup product. Because we have a cup product between A, B, and the dual of C. And then cup products are really well behaved under tensor products. You can actually, if you just take A tensor B tensor C, and then A prime tensor B prime tensor C prime, we can define a cup product on them that just takes A cup A prime, tensor B cup B prime, tensor C cup C prime. And as long as the original three cup products down here satisfy the Leibniz rule, then this cup product up top on the tensor complex will also satisfy the Leibniz rule. And so that basically means that across these three quantum codes, we automatically get a cup product just because within each of these three columns on the tensor factors, we have a cup product. And since these are now like higher dimensional cochain complexes, we can stick our qubits at level 1 of these cochain complexes and we're protected against both X and Z errors. Then we have a cup product across all three, so we get transversal CCZ gate. Oh, script D? Oh, that's a good question. So it's essentially like a cochain complex you kind of get by like multiplying A, B, and C. It's like another way of saying that is if you take the product of like A, B, and C dual, like the pointwise product of these three classical codes, you get another classical code. And then it's the like cochain complex associated to it. Or maybe there's like a dual in there, but it's basically. Cool. Yeah, so this is how we get a cup product and hence like a transversal CCZ gate from classical codes with a multiplication property. So that's how we prove this theorem. And as I described earlier, this theorem kind of using our polynomial evaluation codes immediately gives us like our main constructions of LDPC or almost LDPC codes with transversal CCZ gates. And so it's kind of nice. We get like kind of our results as a black box application of this general result. Of course, the drawback of this is that our three-dimensional tensor product code has a relatively low distance. So I guess maybe the real drawback is that we only have n to the 1 minus epsilon dimension for our LDPC construction. But like the drawback that I haven't talked so much about yet is that our distance is only n to the 1/3. And as Ewan mentioned yesterday, kind of they have a very nice result improving the distance all the way up to almost linear, though the number of logical CCZs drops back down to a constant. And actually building on some constructions from Guan Yu, we actually kind of also had a construction that achieves like distance n to the 2/3 and dimension n to the 1/3. So this is actually, this one down here is like strictly worse than their construction because you can just take like n to the 1/3 copies of their construction and recover these parameters. But I'll kind of briefly say a couple words about both of these constructions just to say kind of the different types of techniques that you can try to use to improve the distance and like what are the challenges that you face. And really the key idea is kind of to do what people did with quantum LDPC codes without CCZ to get the distance high, which is to take these like fancier products, not tensor products, but like balanced or lifted products. So it was a long-standing barrier on in just the construction of quantum LDPC codes without CCZ to improve the distance beyond square root of the block length. And the intuitive reason for this is that people were just taking tensor products of one-dimensional cochain complexes. I mean, this isn't the only thing people were doing, but this was some of the best known constructions like 10 years ago. And the problem is that this tensor product of two cochain complexes, or like a hyper-F product code, will always have logical operators supported within a single row or a single column. Which means that the size of these logical operators is at most the square root of the block length. And kind of this was resolved by this beautiful line of works, which quotiented the tensor product by like some action of a group. So intuitively, we kind of like will associate kind of different qubits along the, like we take some group action and then we kind of associate different qubits that are relayed by this group action. So for actions kind of like walking diagonally through our grid, then like for different squares here that are the same color, we require our logical operators have like the same value along all boxes here of the same color. So it's like a very high level intuition, but intuitively we just kind of like twist our product. We like quotient out, we require like our logical operators to have this diagonal type symmetry. And then this breaks the row and column structure of the logical operators in the hyper-F product. So actually this intuition, you can like use this intuition to like write down a candidate construction of quantum LDPC codes with distance like beyond square root n. But it's also like another question to actually prove this. And this was done like this, first done by this like really nice work of Panalev and Kalichev, where they applied some like robustness property of the underlying classical codes to prove that this sort of like twisted or like balanced product has linear distance. And in terms of that, we can't just naively do the same thing with LDPC codes with CCZ gates, because for these algebraic local codes I described, like these polynomial evaluation codes, they actually weren't known to satisfy the robustness property that we need to have good distance for quantum LDPC codes. So the distance analysis breaks down if you just try to apply these like balanced or lifted products with these algebraic local codes with the multiplication property. So the way that Yiming, Zimu, and Ziwen solve this problem is actually just to prove robustness for these algebraic local codes, which it's like a very beautiful result in of itself. And the one thing is they still have this constraint counting issue I mentioned kind of earlier in the talk. So they're still not able to obtain like a large number of logical CCZs. They kind of have to like plant a repetition code and then they get like at least one logical CCZ. But that's why they end up with these parameters like almost linear distance, but just like one logical CCZ. Something we can also do using like an earlier work of Guan Yu is to get like distance n to the 2/3 by actually not using algebraic local codes at all. So if you're not going beyond like the k times d is greater than n regime, if you're still in k times d is less than n, you could kind of hope to have an analog of a classical repetition code and then not use any algebraic structure. That's what we can kind of do here. We can like observe that CZ is like 2/3 of the way to CCZ. And like every CSS code has transversal CZ, because every CSS code is transversal C naught, and then you dualize one of the two code blocks and you get CZ. So we can kind of like trade off this, like the linear distance of good quantum LDPC codes without CZ, but with CZ, and like kind of reduce the distance, but increase, like upgrade CZ up to a CCZ. So if you don't want to use like algebraic structure at all, this is something you can do. But you get worse parameters than this really nice result up here. Yeah, I think in terms of like, high distance, like distance beyond square root n, quantum LDPC codes, this is, with CCZ, this is basically what's known. And what's interesting is like, these constructions all like pay to roughly equal to n. So they really don't go beyond the parameters of a classical repetition code, which seems like a pretty big barrier. In contrast to our high rate codes, which had like k times d is like roughly n to the 4/3. Cool. So just to summarize, these were our main constructions. These like quantum LDPC or almost LDPC codes with like almost constant or constant rate and distance roughly n to the 1/3, supporting transversal CZ. And yeah, of course, the natural open question is whether we can get like truly good parameters, or like how close can we get to truly good parameters. So like how close can we get to like a quantum LDPC code with linear dimension, linear distance, and constant check weight. And it feels like we have like some of the ingredients we need. Like we know how to get like the number of logical CCZs high. We just, as I just described, there's also known techniques for getting the distance high. So it kind of feels like we just want to combine all these different techniques. But yeah, I guess it's just a technical problem. And you could imagine combining all these techniques and get like n to the 1 minus epsilon, n to the 1 minus epsilon. Getting truly linear might need some like really new ideas, because actually the classical analog of this question, where you just want a multiplication property, isn't known. So it actually does seem to be like a lot more work to getting here. But yeah, that's all I've got.
Okay, thanks, Louis. Time for questions. Yeah, Jung.
This construction is like high-rate version of, say, Guanyu's or Ryohei's construction in some sense, or?
Sorry, which one of Guanyu's constructions?
Like CCZ using like a 3D.
Yeah, so yeah, I see. Yeah, so I think morally, yeah, I think the main difference is we're using these classical algebraic codes to really get the high rate.
So compared to like actual distillation or like factory cultivation scaling, like is it giving some advantage? Is there a concrete kind of example where it's kind of working, or a small size?
Yeah, that's a great question. I think that's currently missing. I think in part because we don't have good enough constructions at this point. There's been some like nice works out of like Harvard, like this paper by Varun Menon and collaborators that get reasonable parameters for like finite size LDPC codes with CCZ. I think, yeah, they have some codes that are like, there's some codes that are like twisted Tora codes and some that are actually go beyond twisted Tora codes. And it seems like their techniques are close to being competitive for like magic state preparation. But I don't think it's like there's been an end-to-end demonstration yet that you can like outperform the best known other techniques for preparing magic states.
Okay, more questions? David?
I wonder if this constraint that the CCZs are disjoint is like too strong, because there can be products of CCZs that like look like they're overlapping, but if you conjugate it by a Clifford, you can kind of disentangle them in a certain way.
Right.
So yeah, like, do you think maybe that's because you're asking for the strong, like this condition is too strong? Maybe that's why you can't break some of these barriers, or?
Yeah, that's a great question. So actually the way we formally like in the paper, the way we formally define like number of disjoint logical CCZs is we say you can choose your logical basis however you want. You can zero out whichever subset of the logic qubits you want. And only then do you count like the number of disjoint logical CCZs. So that's kind of, it's allowing you to apply like an arbitrary circuit of C0 gates to change the basis. So we are somewhat allowing that. Yeah, maybe like I should allow like an arbitrary Clifford circuit or something.
Okay, okay,
yeah.
thanks.
Yeah, we still have time for more questions. Anyone? There was one thing I was going to ask actually. So in this kind of construction to get the quantum property for CCZ, you use this multiplication property to kind of satisfy the cup product. But you could imagine like a more direct quantum version of the multiplication property that's just saying like the sort of dot products of things that produce Z stabilizers on the third code are like inside the stabilizer group again. Do you think there's any way to like skip the cup product to get more general instructions?
Yeah, that's a great question. So actually there are these works that have that are not LDPC, so like that don't have low weight stabilizers, but still transversal CCD. And a lot of these I actually don't know how to put into a cup product framework. Like it seems like I actually haven't been able to construct a cup product from them. And actually even some of them, I didn't really mention it, but there's even ways to like get subsystem codes with low weight gauge operators that can still have fault tolerant error correction, but still transversal CCD from these like non-cup product techniques. So definitely yes, if you're willing to go beyond just like codes with low weight stabilizers, which I guess says like maybe it's possible with low weight stabilizers too. I just haven't seen a way to do it.
Right, that's interesting. Yeah. Anyone for a last question? I think we can thank Louis again for a good talk.